All right. Good morning, everyone. Sorry for the delay. Miss Lily, our dog, just threw up on the couch. I was just too much noise going around, so I couldn't log in trying to clean it. All right, I'm back. For the person whom I was communicating with regarding credit transfer, I never received your email. And if you have that email, forward it back to me. Let's see why I missed it. And all right. So we have the exam, the final exam on Sunday, I believe, and I believe two of you are going to take it on a Friday, unless you all can take it on a Friday. So it doesn't really matter to me. I can split it into two. All right. Last time we were talking about Lyapunov function. Lyapunov function is really an important tool in looking at stabilizing a non-linear system or linear system for that matter. And it's very important tools, as I said, and sometimes it is very beneficial when other method cannot be used, like when you have a center. When you have the eigenvalue of a matrix, the magnitude of them is 1. That means the system is stable. For the nonlinear system, nothing can be concluded from linearization. So sometimes the Lyapunov function can do the trick for you. All right. So last time we had this theorem. You have a V. You have, let's say, 0 is the equilibrium solution. So you have V0 equals 0. Vx is positive. Is x not 0, different from the equilibrium solution? And del V less or equal to 0, then the 0 solution of 6.11 was stable. But if del V is strictly less than 0, then the 0 solution is asymptotically stable. And we saw last time we saw that for example, I'm gonna take an example here. If I take xn plus 1, we did this last time. Xn plus 1 equal to x square of n xn0 equal x0, or x0, may I say. Let's start with 0. And then we saw that x star equals 0 and 1. And let's take a look at x star equals 0. And we took Vx of n was x squared of n. And then del V of xn is x squared of n plus 1 minus x squared of n. That is x4 of n minus x squared of n. And that is x squared of x squared minus 1. So this is less than 0, okay, for x belong to minus 1, 0, union 0, 1. Or the set H is all x in R, where x belong to minus 1, 0, union 0, 1. So if x naught belong to H, then x equals 0 is asymptotically stable. Well, so the stability really depends on where x0 is. Okay? So, any questions so far? All right. So now, if the asymptotic stability does not depend on x naught, then we say x star is globally asymptotically stable. And GAS, that means it's globally asymptotically stable. So we have a theorem for that. Okay. All right. And let me get my notes straight here. Okay. All right, let me take a look at the following. It is hard to manage loose leaves, as I guess. All right. So we have a definition and 6.12. 6.12. Let me see what 6.12 is. Yeah. So let's take a look at, consider xn plus 1 equal f of xn, x x0 equal x naught. Okay. And this is for n bigger or equal to 0, and this is 6.12. Okay. And we're going to assume x star equals 0. That is f of 0 equals 0. So x star of 0 is globally is an equilibrium solution. All right. So now let's see a definition. Yeah, I'm still looking for my notes. 240, 241. There we go. All right. So now assume x star equals 0 is stable if x of n, and this means n0 x0 goes to 0 as n goes to infinity for every n0, for every x0, then we say the 0 solution of 6.1.2 is globally asymptotically stable. So that is globally asymptotically stable. All right. Okay. I am looking for an example good example to do. Okay, let's take a look at an example. Let's consider, this is example 6.8. So we're gonna have xn plus 1 equal yn minus x squared of n yn, y of n plus 1 equal to xn minus x cubed of n. Okay. Now clearly xn plus 1 equal x and yn plus 1 equal y implies x star equals 0, y star equals 0. So we have 0, 0 as fixed point. Okay? You can verify. Okay. Now, let us take a look and let us study the, so this system, xn plus 1, yn plus 1 is equal to 0, 1, 1, 0, xn, yn, plus minus x squared and yn, and minus x cubed of n. Okay? So I'm going to do the linearization. I'm going to try to show you the importance of a Lyapunov function. Okay? So now, so we wrote it. So we have the system, we have xn equal axn plus gn. You see that? And here a is 0, 1, 1, 0. So, and if I look at a minus lambda I, that is minus lambda 1, 1 minus lambda, and that is lambda squared minus 1 equals 0, implies lambda equal plus or minus 1, or lambda equal 1. And this is lambda I, for I equal 1 and 2. All right? So, xn equal a, equal axn is stable. Hence, linearization theorem and let me tell you exactly which theorem. (5.71), okay, gives no information about the stability of our original system. And I mean the original is this. This is the original system. So linearization gives no information. However, if the eigenvalues were strictly less than 1, then linearization tells us the equilibrium solution, which is the origin, is asymptotically stable. But unfortunately, that is not the case. So now we are going to try a Lyapunov function. Okay? So let's try the method of Lyapunov function. Okay? So I am going to take, let v of xn, yn equal to x squared of n plus y squared of n. I'm going to ask you to compute. Take a few minutes and do that. Compute that. See what you get. Okay? So del v xn yn equal x squared of n plus 1 plus y squared of n plus 1 minus x squared of n minus y squared of n. Now, xn plus 1 is this one. So yn minus x squared yn. A plus y squared n plus 1, xn minus x cubed. Minus x squared of n minus y squared of n. I'm gonna depose of the n just to save time and space. Okay? Oh, this one is a square too. Okay? So this one is y squared of n of 1 minus x squared of n squared plus x squared of n 1 minus x squared of n squared minus x squared of n minus y squared of n. Do you see that? So factor 1 minus x squared of n square, you're gonna get y squared of n plus x squared of n, okay? Minus x squared of n plus y squared of n. Now factor this out. So if I factor x squared of n plus y squared of n now, I got 1 minus x squared of n squared minus 1. You see that? Okay. Now let's simplify this. And this one's gonna be 1 minus 2x squared of n plus x4 of n minus 1. And that is x squared of n, x squared of n plus y squared of n times this and this cancel, and I factor x squared of n, so I have x squared of n minus 2. There we go. Okay? This is positive. This is a positive. Now, we want this to be less than 0, so this is less than 0 for minus square root of 2 less than x less than square root of 2. So, hence, if we let h equal to the set xy belong to R2 such that minus the square root of 2 less than x less than square root of 2, then, okay, so h has to be RK, and it's not, okay? That means for any, so 0, 0 is not in here, all right? X is, but Y is not, all right? So if we require X naught 0, 0 to be in here, which is not, then this is asymptotically stable, but not globally asymptotically stable. Globally asymptotically stable means there is no restriction on H, no restriction at all. Okay? So H has to be RK. All right. All right. So now I'm gonna address something. So you did here consider globally asymptotically stable. So we did this one. All right. So let's take a look at this is theorem. Okay, so before I do that, I need to look at some concept. Okay, before I do that, before I don't want to do the theorem yet. Okay, I have a definition, and this is definition 6.1.6. A function v from a set D to R plus is said to be radially unbounded if v of x goes to infinity as x goes to infinity. Okay? Okay? So this means that v of x equals some constant c. Whatever v of x, if this is true, then v of x equals c or closed curve. Okay? This is what it really means. Let's take a look at a function. For example, the other one in here, in the previous example here, this one, we took, what did we take v to be? You see, in this previous example, in this one here, v of xy equal x squared plus y squared, that goes to infinity as the norm, which is x squared plus y squared goes to infinity. So this is radially unbounded. It is radially unbounded. Okay? All right. Here's an example. Example 6.6. Let's take v of x1, y1 is x1 squared over 1 plus x1 squared plus x2 squared. Okay? X1, x2. Okay? So v of x1, x2. We need to show this one as x1, x2 goes to infinity. All right? If I take so let's try the level set. Okay? All right. So try the level set. So let's set x2 equals 0 and vx1 0 equal 1. This is the C. That implies x1 squared over 1 plus x1 squared equal 1. Okay? But cannot hold. Can't hold. Why? Try. You have x1 squared equal 1 plus x1 squared, you get 0 equal 1. So that is bogus. So v of x1, x2 is not radially unbounded. Okay? So this is not radially unbounded. Not. It has to be on a level curve. So the function has to be, you see, this is v. Has to be a closed curve. Because I took vx1 0 equal 1, that means this one equal 1, but that is not, that give us a contradiction. So therefore, this function does not belong to closed curve. However, this one does. You take x squared plus y squared equals c for any c. And what is this is a circle centered at the origin with radius square root of c. Okay? So this is okay. Now, let's try the norm. So let's define so again, we have v of x1, x2 equal x1 squared over 1 plus x1 squared plus x2. So let's try the concept. Okay, let's try this. So let's try x1 0, 2, that is a square root of x1 squared plus 0 squared. This is the norm of that. Okay? So that goes to infinity. You see, that goes to infinity. However, the limit of x1 goes to infinity of v of x1 0 equal the limit as x1 goes to infinity x1 squared over 1 plus x1 squared equal to 1 different from infinity. So all you need to do is, if it's not radially bounded, set one of them equal to constant or 0 and see what the limit gives you. Okay? All right. I'm looking for theorem 6.12. Sorry, guys. All right. So now we have the following theorem. Okay. This is theorem 6.13. Assume the hypothesis of theorem 6.12 holds with D equal to Rn. Okay? Or Rk. In addition, if V of x is radially unbounded, then the zero solution of 6.1 upon 2 is globally asymptotically stable. I will not prove it here, but I have a nice proof for it in the book. Okay? All right. We can do some examples. Here is an example. And that is example 6.7. So let A less than 1, and we're gonna take a look at xn plus 1 equal A xn sine of xn with x0 equal x0 and bigger or equal to 0. Then x star equals 0 is an equilibrium solution. Okay. All right. And if I let v of xn equal x squared of n, then v of 0 equals 0. V of x is positive if x is not 0. Now, this is a scalar equation. It doesn't have to be system. V of 0 equals 0. All right? Now, let's take a look at del v of xn. That is x squared of n plus 1 minus x squared of n. That is minus x squared of n, and that is less or equal a x squared of n minus x squared of n, and that is x squared of n a squared minus 1. So here d is r minus 0, which is good. So that is satisfied because here we have a scalar. Of course, we need to exclude the because d, the set d does not, okay, verify this. Okay, so, and I'm looking at theorem 6.12, and moreover, v of x, which is equal to x squared of n, goes to infinity as x goes to infinity. So v is radially unbounded. And by theorem 6.13, x equals 0 is globally asymptotically stable. Okay, there's no restriction on that. All right. Any questions? Now let's take a look at the domain of attraction. This is a very important concept in engineering. Okay. Definition of 6.17. Domain of attraction. Okay. Assume V of x is a strict Lyapunov function in D like H here, I'm using D, then the domain of attraction, of an equilibrium solution of an equilibrium consists of all points such that a solution starting at them tends to the equilibrium. Okay. So thus, if V is a strict Lyapunov function on a set D equal Rn, then the origin is asymptotically stable, and the domain of attraction is n star equal to all the point x in D such that V of x less or equal to C for positive constant C. So please take a closer look on this definition. Okay, take a look at it. So we must have stability first. Did I hear someone ask a question? I'm gonna do an example and show you what's really going on here. Okay. All right. So let's take a look at an example. Again, that is example 6.9. So we're gonna have xn plus 1 equal x2 of n minus x2 of n square root of x1 square of n plus x2 square of n plus 1, and this is x1. x2 of n plus 1 equal x1 of n minus x1 of n square root of x1 of n squared plus 1. Clearly, 0, 0 is an equilibrium solution. It's the only one. Okay? Let me see if there are any question here in the chat. No. Okay. So linearization is inconclusive here. That means if you write it as xn equal a, xn plus 1 equal a, xn plus gn, it will not work. That theorem I mentioned today at the beginning of my lecture will not work because the matrix A is 0, 1, 1, 0, so lambda R1. You see that? Okay? So it fails. So linearization is inconclusive. So we're gonna take let V of xn y, sorry, x1 y1. I don't know why I do that. Equal x1 square of n plus x2 square of n. And so del V is x1 square of n plus 1 plus x2 square of n plus 1 minus x1 square of n minus x2 square of n. Okay? Now, replace this there. I'm gonna take x2 square of n, and I'm gonna have 1 minus x1 square of n plus x2 square of n plus 1. The same thing from here, I'm gonna have plus x1 square of n, and I'm gonna have 1 minus the square root of x1 square of n plus x2 square of n plus 1 minus x square of n minus x2 square of n. See what I did? I replaced x1 of n plus 1 squared, but immediately I factor x2. This became x2 squared, and then you are left with 1 minus the square root of that square. Yes, square. Okay? How's that? Now, this is 1 minus the square root of x1 square of n plus x2 square of n plus 1. And I'm gonna have x1 square of n plus x2 square of n. You see that? Minus x1 square of n plus x2 square of n. Let's factor this out. So that is x1 square of n plus x2 square of n. And then it's gonna be 1 minus, oh, by the way, this is a square, sorry. 1 minus the square of x square of n plus x2 square of n plus 1 square and minus 1. Okay? You see what happened? So what is that? Okay? Um, I'm redoing it here. I'm trying to look at my note. Let's see if we can make any sense out of it. Okay? So let's see what this is. X1 square of n plus x2 square of n 1 minus 2 square root of x1 square of n plus x2 square of n plus 1 okay plus x1 square plus x2 square plus 1 minus 1. Okay? And let's see how we can deal with this. Now, this 1 and this minus 1 go away. Do you agree with that? So I am left with x1 square of n plus x2 square of n. And I'm gonna have a square root of x1 square plus x2 square plus 1 times the square root of x1 square plus x2 square plus 1. That is this one here. And minus 2 the square root of x1 square plus x2 square plus 1. See what I did? It's a clever way of writing this. Now, let us so del V of x1, x2 is this, which is x1 squared plus x2 squared. Now let's factor this out. Times the square root of x1 squared plus x2 squared plus 1 minus 2. There we go. Okay? What do you think? It's a really clever way to do it. Now, this is positive. This is positive. So we want the square root of x1 plus x2 squared plus 1 times square root of x1 squared plus x2 squared plus 1 minus 2 less than 0. This is if and only if this is if and only if a square root of x1 squared plus x2 squared plus 1 minus 2 less than 0. So I am trying to find the attraction. Okay? So which holds for x1 squared plus x2 squared is less than 3. Okay? What you need to do here is just square both sides. Square both sides, you get x1 squared plus x2 squared plus 1 less than 2 less than 4. So you get x1 squared plus x2 squared less than 3. You see that? So this holds. So the domain of attraction is n bar equal to x1, y1 belong to R2, x1, x2, such that x1 squared plus x2 squared less than 3. Or this is the same as x1, x2 belong to R2 such that v of x1, x2 less than 3. So that here is your C. So this is the domain of attraction. So that is the domain of attraction. Okay? How's that? You see how much work we did to get to it? Any questions? Now we're gonna talk about instability. I have only one definition or theorem, and I will do that. Let's take a few minutes break and come back. Not much. Okay? All right. So this is was the domain of attraction. All right, so this is theorem 6.1.4 about instability. Let X star be an equilibrium solution of 6.1.2 let U be a neighborhood of X star. Suppose V is from U into R plus is continuous on U if Vx star equals 0, but there are points arbitrarily close to X star where V is strictly positive and that del V of X is positive on U minus X star. Then X star is unstable. For 6.1.2. Okay, so let's do an example and see how things work. Here's an example. So we're going to have xn plus 1 equal y minus x4y. We are suppressing the n. And yn plus 1 equal minus x cubed y squared. So here we're suppressing the n. There is an n and n and n. So 0, 0 is the only equilibrium solution. So we're going to let V of xy equal x squared of n plus ys squared of n. Then V of 0, 0 is 0, and V of xy is positive for xy not 0, 0. Okay? Now, So we have Vx star equals 0. Okay. And there are points on V where it's strictly positive. So now we're gonna take a look at del V of xy, that is x squared of n plus 1 plus y squared of n plus 1. That is y squared 1 minus x4 squared minus x squared of n minus y squared of n plus y squared plus x squared plus x squared. That will be 1 minus 1 plus x squared y squared squared, because you have the minus and you are squaring, and minus x squared minus y squared. And if you simplify this turned out to be x to the 8 y squared plus x to the 6 y4, and that is positive for xy different from 0, 0. Okay. So here the set u equal to u. So here u is all r minus 0, 0. Okay. Or may I say R2 minus 0, 0. The set u. Okay. And then look what we have. Strictly positive and del V on u. So del V on this set u, which is R squared minus 0, 0, is strictly positive. So therefore, by theorem 6.1.4, 0, 0 is unstable. Note that theorem 5.71 is inconclusive. This is linearization. So linearization does not work here. This is another example. Why linearization does not work? Because the matrix A is 0, 1, minus 1, 0. So if you look at the lambdas equal plus or minus 1, so the lambdas are 1. So linearization does not give an information about the nonlinear system. Linearization tells you if this is unstable, then the linear system is unstable. If this is asymptotically stable, then the nonlinear system is asymptotically stable. But here, lambda equal 1 mean this one here, the linear system is stable, neither unstable nor asymptotically stable. So it gives no information either way. Okay? I'm stopping here. I think we had a very productive day. Tomorrow I will meet with you for the last lecture. And we have the exam. 2 people are taking it on Friday and the rest on Sunday. All right. We'll talk to you later.